Hey all, we are going to have a live online deep dive session on a specific topic of internet working. And this session is totally free. For the topic, for the timing, please click the link below and register. So these are the topic of discussion for today. We are going to quickly do a recap of OSI model, and then we will. The focus of discussion today, as the topic tells you, is about the data link layer. So we'll go focus more on the LAN. What is a shared medium? How the CSMA CD works, which is a rule on how do you when there are multiple PCs in the same shared network, how do they access it? And finally, how does a PC communicate to another with a switch in between? So this is going to be a lab. So that with that we will conclude this 30-minute session. So let's get started. Let's start with the first topic, which is we will do a quick recap of OSI model. So let's come to this particular slide. Again, I have already posted the link in the YouTube video about this, but you can see that there were two major models that has actually come into the play. And why we needed a standard was because when internet kind of exploded, we understood that there were a lot of business opportunity. A lot of vendors started building the equipments to build the network, which includes switches, hubs, routers, firewalls. And each vendors who was actually having expertise started implementing things in their own way. So uh, uh, that is where we understood that there is a need of standard, because when there are multiple devices in the internet, for example, if you see how an internet is being built, this is actually built by through multiple devices, and each of these devices needs to kind of interoperate with each other. That is where we really need something as a standard, and that's how the TCP/IP and OSI standard came into picture. There is something called a protocol war on a competing OSI model competing the TCP/IP model. I have put a video of that already in the YouTube channel as well. Now, let's again the most important item for today for our discussion is about the TCP/IP model. So, sorry, the data link layer, and we will just have a quick recap of the TCP/IP model. First of all, the application. Application is basically deciding the application layer of a TCP/IP model defines how an application should interact with the user at the application level. An simple example is HTTP or HTTPS. It is having some set of methods in HTTP, HTTPS. For example, let's say there is a request coming to the server to show the content of the web server, right? Like let's say you open Facebook, there you can, if you go deeper and then see what is actually happening, there is a get request to show all the information. If you want to send some information, let's say you want to post a text or something in Facebook or any of the social media kind of servers, then there is a post method. So at high level, the application layer defines how a user should be interacting with the application and what are the rules of the applications. At the transport layer, again taking the HTTP as an example, it says the application layer tells to transport layer that, you know what, for my application, what I need is a protocol in the transport layer. And there are two major protocols. One is TCP and another is UDP. So the application layer defines or decides and tells the transport layer what protocol to use. Not only a protocol, it also tells use this protocol, TCP or UDP, and then it also tells that I want to use a specific port. If it is HTTP, then it is going to use port 80. If it is HTTPS, it is going to use port 443. So it actually defines that. That's what the responsibility of transport layer is. And what happens is when an application is actually running in a server, these ports actually will be in listening mode. It has to listen to this particular port, so that some request comes from internet to this application, and if it reaches the TCP port 80, then it understand, okay, it is for the application HTTP, right? That's how it is actually designed. Now that is about transport layer, and in the network layer, the responsibility of network layer, if you go back to the slide here, P is responsible. Let's say this PC has to communicate to the server here, which is actually using HTTP. How do this PC reach all the way from here traveling through the internet, how do I reach the application? That particular process, that is actually the responsibility of the that is actually the responsibility of the IP. So what does IP do? What does IP do is simple. It actually defines the protocol, or defines the rules on how do I send the packets across. So IP tells that how should the packet be sent across the internet. That's the responsibility of IP. Okay. Uh, Coming on to the next layer, which is a layer that we are going to discuss more today, which is called as the data link layer. So what do data link layer do? Its responsibility is, so as I told, IP is responsible for sending the packet across the internet and finally making sure that it actually reaches this application server. What this guy data link layer does is, its responsibility is only between this node to this node, this PC to this router, or maybe this router's this link to this link. So basically, it only takes care of the rules and procedures on how a packet should be sent in a specific link. When I say link, it is called as this particular link, one end to another end. And that is the focus of today's discussion, data link layer. Okay. So we just had a recap only till now. So we will go back and then we'll do data link layer. As I mentioned, what is a LAN? So the data link layer, and what is the connection of data link layer and LAN is. Data link layer is mostly used in the LAN technologies. What that means is, in a LAN, how do you communicate is actually a responsibility of the data link layer. There are a set of protocols there, which we are going to go in a short while. But do understand, when you first define LAN, LAN is nothing but a segment where you can connect multiple devices together. So in this case, what I defined by LAN is that particular one line you see there. That is what the LAN is, and you can see that this is actually kind of a shared medium. This is not going to be the a line as such. What it will be is a switch wherein you will be connecting all these devices. Okay. But again, do understand that this is going to be a shared medium. And what does a shared medium means? That means all the species has to make sure that they are, one of them only will be using this medium at one point in time. You cannot use multiple devices cannot use the shared medium at same point in time. Now there is a concept called duplex and half duplex and full duplex, which wherein there will be some differences in the definition I told. But as of now, just understand that when you call as a shared medium, that means only one PC can actually uh, communicate at one point in time. Now, coming back to the LAN technologies, we are having three major technologies that you need to be aware of. One is Ethernet technology, another is token ring, and another is FDDI. But we will be focusing on Ethernet only as of now, because that is the most standard and mostly used one. Token ring and FDDI is not that much used anymore in this time zone, in this time frame. This is a little bit of history on the evolution of LAN. I have already put a video of that as well. It is not really important for you to know about it, but it's always good to know which all are the companies that are actually working on and building this LAN technology. For example, DEC and Intel and Xerox is one of the three major companies we were actually building this, contributor in building this technology. Okay, now let's see. So we talked about the shared medium. We talked about LAN. What LAN is: a collection of devices connected to the same segment. It doesn't need a router or anything to communicate. It can actually communicate in the same LAN segment itself using the data link technology. That's what a LAN is. Now we also talked about a shared medium. So how and what are the rules for getting access to a shared medium? So these are the rules. So before we get into this, the rules of shared medium, let's see how these packets are actually sent across in the data link layer. So let's take one PC who wanted to send data from this PC1 to PC2, and let's take a simple example of HTTP again. What is encapsulation? Again, I have a video already in that in the YouTube. I will be able to put that as a link as well if it is actually helpful. But do understand that at the application, let's say this PC1 is communicating to PC2 over HTTP. Now, at the application layer, it defines, okay, HTTP is my protocol. And at the transport layer, as we mentioned earlier, it understand, okay, for HTTP, I have to use port 80 and TCP is the protocol. What happens once the HTTP data is come to the transport layer is the HTTP data is encapsulated in TCP header. That what that means is the data will be appended with TCP headers. And then that whatever header it has to add, TCP will add those headers, and then the data will come to the IP. At the network layer, IP will use its own headers and then use the data, which includes TCP and HTTP, and then it actually sends that down into the data link layer. At the data link layer, assuming Ethernet is the technology that they are actually using, what it does is all the content, IP, TCP, and HTTP, will be encapsulated in that. And what data link layer uses to identify the devices in the network is the MAC address. What is a MAC address, how it is structured, we will have a separate session on that. But right now, understand there is something called MAC address, media access control address, which is actually on the Ethernet card. Again, we are going to talk about the Ethernet card. It will be hard coded in the Ethernet card. You can actually check your MAC address by sending a command on your PC, which we will talk about in a moment when we do the lab. But do understand there is a MAC address. So how this PC understand this PC is identified in the LAN segment using a MAC address. And similar way, PC2 is identified by its own MAC address. So the header, and we'll go into the header of what the Ethernet header contains. The Ethernet header will be having the details about the MAC address of PC1 and PC2. How do PC1 gets the MAC address of PC2? That is again a separate protocol is being used. We will see that in the lab. Now, this particular piece, when it comes to the data link layer, even though it is the original HTTP packet having the TCP and IP headers, when it reaches the Ethernet and the data link layer, we call that as frames. So do remember talking about frames. Now, once you create the frame, it actually goes and sends it into the NIC card, because NIC card is basically where you actually plug in the what is it called? You plug in the cable. You'll be able to see the RJ45 cable where you will be plugging it in so that your PC gets connected to the LAN. Your PC may be connecting through the Wi-Fi also, but as of now, since we're talking about Ethernet, let's talk about connecting using a cable. Now, once that happens, is every Ethernet card will be having something called a sending queue. So it actually puts those packets into the sending queue, and once and then the driver in the um, interface card will be selecting those packets to send it out. So now what happens is it doesn't immediately send the packet. So let's say this is a PC which wants to send the packet. But what happens is before it sends the packet, it goes and does something called sensing the carrier. What it is doing is it is checking whether since this is a shared medium, is somebody using this particular shared medium already? That's what it is trying to do, and that procedure is called as sensing the carrier. So if there is any electrical signals already there, if it doesn't see any data being sent there or doesn't sense any carrier, it doesn't immediately send the frame. It actually waits for something called inter-frame gap. And why that is actually needed is because when the packet is actually receiving at the receiving end, the interface cards need some time so that it actually collects the complete packet. So it doesn't immediately send, it actually waits for inter-frame gap. And if there are multiple packets or frames to be sent in the data link layer, it actually again waits for inter frame gap, so that at the receiving end, it is able to have the interface card is actually having something called a recovery time. Now you don't CCNA may not, you may not need to know about interframe gap, but it's always important to know about interframe gap. The reason behind is when you talk to an interviewer about this, he knows that you are having a deeper understanding of that. Also, for your understanding as well, it is always good to clearly having a deeper understanding of how things actually works. Now, these are the benefits of a major benefit of interframe grab is it is the recovery time of the interface card because it needs it need a small time for before it actually process the next packet. And that small time, it actually varies. For example, on a 10 Mbps, it is 9.6 microseconds for 960 nanoseconds for 100 Mbps, and it is 96 nanoseconds for gigabit Ethernet. So it's not a huge wait time as such, but still it is actually required so that the network interface card has something called recovery time. Another thing that you wanted to talk about when you talk about carrier sense multiple access is about differing, the concept called differing. What that means is when this PC, let me use this, this uh, pen to illustrate that when the PC is actually trying to access this, and let's say there was already some signal that's actually going on. In that time, what happens is it doesn't immediately send the packet, because if it sends, then what happens is there is already a signal going on. And if it again sends it, then the signal will get corrupted. So it actually it does something called differing. So this is a word that you need to know, which is as differing. It doesn't immediately send. If it senses the carrier, then it actually waits. Instead of saying wait, what we call it as is we um, sense the carrier. We defer it. Instead, we sense it, and once we identify there is a signal, we defer it. Um, okay, so now let's go to what to the next concept. Let's say now what happens is this PC, which let's call him as PC1. PC1 is sending wanted to send some traffic, and it is actually already it sends the traffic, it sends the carrier, and this is another PC which is actually PC3, and both of them want to communicate to, let's say, PC2. Okay, this is the scenario. Now what happens is PC1 tries to send the packet, sends the carrier, and at the same time, PC1 also senses the carrier. So both see that there is no signal in the data link layer, and it actually tries to send the packet. Now, what happens at that point in time is both of them send the packet at the same time. And now what happens is, so there is a signal, if you want to see it pictorially, there is a red signal going on as we see here, and there is a there is a red signal that's actually going on, which is from PC3 to PC2, and there is a blue signal going, which is from PC1 to this particular PC, which means this shared medium is being used by two PCs at the same time. When that happens, that is when we call there is a collision that has actually occurred. That means the signal that is actually sent by PC1 and PC3 is being corrupted. Now, this scenario is called as collision. Uh, Now, what happens when the collision happens is these PCs continues to send some signals so that all other PCs in the network is informed that there is a collision that is actually happened. That particular thing is called jamming, or you call it as you send the jam signals so that other PCs in the network know about there is a collision that has actually happened. So what we learned till now is sensing the carrier. We also talked about differing if there is a signal there. We talked about jamming, which is basically we talked about collision. That is when two PCs sensing the carrier at the same time and send the packet at the same time. There is a possibility of corrupting the signals, and that is called as collision. And finally, we talked about jamming, which is letting all other PCs in the network know about there is a collision actually occurred. Once that collision occurs, what happens is it actually does something called jamming. sorry, backing off. So after jamming, it actually does a backing off. What backing off means is the PCs wait for a random amount of time before it tries to attempt the access to the shared media. And that particular scenario is called as backing off. And that backing off needs to be a random time, because if this PC and this PC wait for the same amount of time and then try to attempt it, what happens? Again, the same scenario will occur. So this PC has to wait for a different random amount of time. This PC has to wait for a different random amount of time, so that the probability of one of them acquiring the shared medium is much, much better. Let's go to the next concept, wherein now it actually what it does, it again attempts again, and if it finds that medium is actually available, it goes and sends the packet. So just to sum up what we have talked about till now, is this concept. Let's just sum it up. Okay, first thing is, and I need a white, please. First thing what we talked about was sensing the carrier, sensing, and then we talked about once it sends, if it is identified that there is a signal already there, then it does a backing off, right? Backing off. And then third, we identified that if both the pieces tries to communicate at the same point in time, then it actually waits, or when it sends at the same point in time, then there is something called collision that is actually happening. So collision. Fourth thing that we talked about is differing, when there is, sorry, jamming. Jamming, right? So jamming is basically once collision is actually happened, then we send the pack some signal for a continuous amount of time, so all the PCs in the network know about it. After jamming, we also talked about differing. Basically, what that means is it actually waits for a random amount of time, uh, waits for a random amount of time before it actually attempts to send again. Time before it attempts to send again. Okay. So these things we have learned. Also, we learned about one more thing, which is interframe gap. Interframe gap. What is interframe gap? It actually waits for a specific amount of time, depending on the speed of the internet, speed of the data link layer, speed of the Ethernet. It actually waits for a specific amount of time. If there are multiple packets to send, multiple frames to be sent, it waits for a random amount of time. How and why it is actually done is because this is required, because the network interface card should have a specific amount of time for the recovery. Fair enough. What else? Now we are actually talking about the slot time. So you may ask, like, when does a PC can say that I have acquired this particular shared medium and this is for me now? The answer for that is once it actually sends somewhere around 512 bits, then you cannot, the other PC cannot say that I also want to access this one. So once a PC sends approximately 512 bits, that time the PC can actually say that, you know what, I have acquired the um, shared medium for myself. Now, what happens at the receiving end? What happens at the receiving end is, again, there is a cable that actually goes and plugs in into the Ethernet card of the receiving PC, and it has something called receiver queue. So it actually gets the packet from the receiver queue. So it actually gets the packet from the receiver queue, and then it actually processes. Now, before I go into detail about how this is being processed, it is important for us to know about the um, Ethernet frame format, right? So this is, as I told in one of the slides, that there is something called, if you remember, there is something called the um, encapsulation that is actually happening, which means at the Ethernet layer, what we do is we use the Ethernet frames to we use the Ethernet headers to encapsulate. So what is that Ethernet header? What does it contain? It contains the preamble. This is how the Ethernet header will look like. It contains the preamble. and start of frame. It contains destination address and source address. What are the destination source address? We'll get into that. It has a length or a type field, which actually tells you what is the upper layer protocol. It has the data field, which is the actual data. Now, this data field will be containing all the above headers and data, which means at the Ethernet layer, it will have the IP header and the data of IP header, and the data of IP header will be having the header and data of the transport layer, so on and so forth. Finally, it has something called frame check sequence, which is the CRC, basically to check whether the frame is not corrupted. So it actually runs a checksum and then see whether the checksum is actually valid or not. We'll go over each of these field of the Ethernet header in deep. But I think right now our time is up. So we are going to resume this in the next session again. We will also go through this particular lab, and what this lab talks about is the what this lab talk about is the uh, this PC is trying to reach to PC2. Now, what happens in the switch and what happens in the PC? For example, if you do show MAC address table, uh, right now it is all empty. But when the moment this PC, and I'm trying to ping this PC, it, let's say it's trying to access the PC2, which is this PC1 is having 192.168.10.1 IP address, and it is trying to reach to the PC2 having 192.168.10.1 IP address. And now when you go and see on the switch the same command, you can see the MAC address is being learned, and it says that on FA02 there is a MAC address so and so, and on FA01 there is a MAC address so and so. How does it learn that? We will cover that in detail in the next session, and I will keep you posted when the next session is going to happen. Thank you. Hope you guys enjoyed this.